What's up, guys? It's Mr. Brengle, and today we are going to talk about momentum in collisions. So there's basically four categories of collisions that we're going to talk about: elastic, inelastic, perfectly inelastic, and explosions. We'll kind of dive deeper into those in the next couple slides. When it comes to collisions, linear momentum is conserved in all collisions, meaning that the initial momentum of the two objects when added together before the collision must be equal to the momentum of the two objects when added together after the collision. Okay? So it's very similar to conservation of energy, where momentum can be transferred from one object to another. Okay? So specifically here, if this is, kind of represents the conservation of momentum. Okay, I'm going to kind of put that conservation of momentum. Conservation of mom. Okay, let's break that down a little bit more. So if there's two objects, we could say that the initial momentum of object A plus the initial momentum of object B must be equal to the final momentum of A plus the final momentum of B. Okay? So when you take the initial momentum of objects A and B and add them together, they should be equal to the momentum of objects A and B on after the collision when added together. Okay? And then we can go even further and we could say, okay, well, the mass of object A times A's initial velocity, this is assuming that the mass doesn't change, okay, plus the mass of object B times B's initial velocity. So this would be, this is the momentum of object A, mass times velocity, and the momentum of object B, mass times velocity. Those would be before the collision. And then this would be equal to the mass of A times A's final velocity. So again, we're just assuming that mass is staying constant, and the only thing that would be changing would be the velocity of the objects. Okay, mass of object B times B's final velocity. Okay, so again, this would be A's final momentum here and B's final momentum here. Okay, so that kind of shows you more or less the equation, the general equation for collisions. Now, we'll kind of adjust this equation depending on the type of collision, but it's all the same in terms of the initial momentum has to be equal to the final. Okay, so let's go ahead and move on and talk about a couple of these. So, kind of got some stuff set up here. We're actually first going to talk about the explosion, which is at the bottom. So when people hear explosion, they're thinking like dynamite, TNT, boom, that sort of thing. An explosion, in the sense of a collision, is simply when two objects start together, like they're connected, and then they move apart from one another. Okay? So, for instance, a Nerf gun, where there's the Nerf bullet inside of the gun, and then you pull the trigger and the bullet separates from the gun, right? So that would be an example of an explosion. Or let's say that there's two people that are riding together in a wagon or on a sled down a hill, and then one person jumps off. That would also be considered an explosion, where they started together in the same object and then one person left. Okay? Now, in terms of elastic, inelastic, and perfectly inelastic, you got to be really careful about enunciating these words so that we know very specifically what we're talking about, because this can get confusing. So let's start with elastic. Elastic is kind of what it sounds like. It's a hit and bounce. Okay, elastic, bounce. So two objects hit and then they bounce apart from one another. And in this case, momentum and kinetic energy are conserved. So the kinetic energy part is important. Okay, we're going to come back to that. Okay, so there's no deformation of the objects, meaning that, for instance, in a car crash, when two cars come together, all the metal gets bent and things break off of the cars and there's pieces everywhere. There's glass all over the road from the windows. That would be deformation. Okay, so the object itself is altered. And that's why true elastic collisions are unlikely in real life, because there's not a lot of situations where kinetic energy is fully conserved. The most realistic example would be collisions of subatomic particles, inside of molecules, the collisions of the atoms. That would be about as close as we could get. Okay. Now, I'm actually going to go over to the blue here, the perfectly inelastic, because this would be the opposite of elastic. If elastic is hit and bounce, then perfectly inelastic is hit and stick. So the two objects hit each other and then they become one object. Okay. So, and that could mean that they stop moving together, or that they connect and then move together as one object. Okay. In this case, momentum, again, is conserved, and it will be in all collisions, but kinetic energy is not conserved, okay? So there's going to be loss of energy due to things like sound and heat when that collision is made, okay? So again, we're going to come back to the kinetic energy part here in just a second. So the most realistic example of collisions, like almost all collisions that you see in real life, are just plain inelastic collisions, and all that's referring to is just that we know that we're not going to have a perfect elastic collision in most situations, and then perfectly inelastic is very situational, like train cars coupling together, or for instance, a football player tackling another football player, and then they move together to the ground. Inelastic is still a hit and bounce. So the momentum's conserved, but kinetic energy is not. So that's why it's more realistic than elastic, because it's very similar. It's just that we're not going to be conserving all of the kinetic energy, okay? It's because there is deformation and internal energy loss due to heat, sound, that sort of thing, okay? So let's kind of draw these out so you have a visual for what this means. With the elastic collision, if I have a bouncy ball and I drop the bouncy ball and it hits, it's going to come right back up to the initial position that it was in, because kinetic energy is conserved. Okay, since kinetic energy is conserved, then that means it's going to go right back up to the same spot. We haven't lost anything due to heat or sound or anything like that. Okay. Now, with a perfectly inelastic collision, what's going to happen is this ball is going to fall, it's going to hit the ground, and it's going to stick to the ground. It's just going to stop there. So imagine like you've got a ball of maybe you got like a really heavy medicine ball that doesn't really bounce when you drop it. It hits the ground and it just stays there. Okay, so that would be perfectly inelastic. Now, more realistic collisions, inelastic. What's going to happen here? You guys, this is real life example. You throw the bouncy ball down, but when it comes back up, it's only going to go up to a portion of its original height, right? Because we've lost some energy. And we talked a lot about this in our last unit, which is why it's nice to do energy first and then talk about momentum, okay? So we'll do lots of, examples and have different simulations and stuff where you guys can visualize this. But so what I want to do here now is I want to look at the specific equations for all of these things, okay? So for elastic or inelastic collisions, the hit and bounce, again, we know that the initial momentum must be equal to the final. So if we have two objects that are initially separate and then they stay separate after the collision, we basically want to write it like this. The initial momentum of object A is plus the momentum initially of B is equal to the final momentum of A plus the final momentum of B. Okay? And these are all, they're separate, right? Because they started apart, they hit each other, and then they move away from one another, okay? So, you could break this down and go through the whole, mass of object A, velocity of object A, initial, etc. This is going to be the exact same equation that I just wrote out on the first slide. So I'm not going to go through that all the way, okay? Now, for a perfectly inelastic collision where they hit and stick, in this situation, you've got the initial momentum of A plus the initial momentum of B. And I know it's kind of hard to tell, but these are supposed to be lowercase p's. Now, since they hit and stick, the way I'm going to write this is the momentum of A and B together. Okay, so in this situation, you have the two objects, they start apart, so the momentum of A initial and the momentum of B initial, and then they come together and stick and move as one object or stop as one object, and that's why I've written them together like this. So we would want to write this more like this. So the mass of A times A's initial velocity plus the mass of B times B's initial velocity is then equal to, the way I'll write this is the mass of A plus the mass of B. So I'm gonna write it as mass AB. You're just adding them together. Okay, times their final velocity. And this would be, A and B together. Okay, so they're really just moving as one object now, which is why I'm trying to write it as just one object, MAB. Add the masses together, multiply it by the velocity that they're both moving with. Okay. Now the explosion would be basically the opposite of that. The objects start together, so the momentum of A and B initial is equal to the momentum of A final plus the momentum of B final. Okay, because in the explosion, they move apart, right? So they start together as one object, and then they become two objects. And we can write it again like this. So we would write the mass of A and B together times their initial velocity is equal to mass of A times velocity final of A plus mass of B times the final velocity of B. Okay, so again, they start together, they move apart. All right, so it's the same idea. The initial momentum must be equal to the final momentum. It's just a matter of whether those objects are sticking together or moving apart, or if they were initially apart and continue to move apart after the collision. So it's just kind of dependent on what we're looking at there, and you'll be able to pick that up from the worksheet or the problem that we're doing. Okay, so now let's get a little visual here. Let's look at this. Let's actually do a little math calculation here. So we're going to start. We've got these red and blue carts here, and they're going to collide with one another. And I have this set up to be an elastic collision. Okay, and I have the initial velocity of cart A at positive 5 meters per second, and then the initial of the blue cart at negative 5. So remember that velocity has direction, so that means that since velocity is used to calculate momentum, momentum must also have direction. So the red car has a positive momentum, the blue car has a negative momentum. Remember that negative sign only tells you direction. That's the only thing it tells you. So you got to kind of remember that from the velocity and acceleration units. And then both carts are 1 kilogram. So if you had to guess when these two carts collide in a perfectly elastic collision, meaning hit and bounce, what should happen to the velocities of these two carts? I want you to think about that. Maybe pause the video and think about what would happen. And then let's actually look at a little bit of math here. So let's calculate the initial momentum of the system, and then we'll calculate the final. So the initial, or the momentum of A initial, this is going to be its mass times its initial velocity, okay? Which is, in this case, is going to be 1 kilogram times 5 meters per second. Okay, so that's going to give us a total momentum of positive 5 kilograms times a meter per second. Okay, so that's A's initial velocity or initial momentum. Okay, now let's look at B. So momentum of object B initial would be, again, the mass of B times its initial velocity. Okay, so in this case, it's going to be 1 kilogram times negative 5 meters per second, which is going to give us a total momentum of object B at negative 5 kilograms times a meter per second. Okay. All right, so again, if you haven't figured it out yet, what do you think is going to happen when these two carts collide and bounce away from each other? Red car has positive 5 kilograms times meter per second of momentum, and object B is exactly the opposite, negative 5. Okay, so what I would expect to happen here is that the momentum of cart A will be transferred to cart B, and the momentum of cart B will be transferred to cart A, so that we abide with the conservation of momentum rules, and they'll basically switch velocities. Okay, let's go ahead and start this and check it out. So they move in, they bounce, and they move apart, and sure enough, those velocities were switched. So now, if we were to look at the final momentum of object A, its calculation would be 1. So if this, in fact, I'll do momentum A final is now 1 kilogram times -5 meters per second, which is equal to -5 kilograms times a meter per second. And for object B, it's the exact opposite. 1 kilogram times +5 meters per second, which is 5 kilograms times a meter per second. Okay, so you can see here that they just switched velocities, and because of that, momentum's conserved, and in this case, kinetic energy is also conserved. Okay. All right. So let's kind of play around with this here, and let's look at what happens when we change, masses and initial velocities and stuff like that. Okay. So if we'll stick with elastic collisions, and all I'm going to do here is I'm actually just going to double the mass. Let's reset this. We'll double the mass of cart 2. So now we're starting with the same velocities, +5 and -5, but this time we have double the mass over here. So if we're going to do an initial momentum calculation for, object A, it's going to be, let me get my color right here. It's, again, just going to be 5 kilograms times a meter per second, 5 times 1. And then on the, again, if I can get my colors here, there we go. And then over here, it's -5 times 2, which is -10 kilograms times a meter per second. So the point of this is that in total, initially, we have -5 kilograms times meter per second of momentum, because I'm adding these two values together. 5 plus -10 is going to give us -5 kilograms times meter per second. So that would be the total initial momentum of the system. Okay. So at the end, we have to have -5 kilograms times meter per second momentum total in the final portion. Okay. So again, let's look at this simulation here. What do you think is going to happen this time? So this one now has more mass, so they're going to bounce. What's going to happen to the speeds of these carts? Okay, I want you to take a second and think about that. Pause the video if you need to. Okay, and then let's look at it. So you can see that because the blue cart had more initial momentum, it transferred its momentum to object A. Okay, and so A moves off with a faster speed than B. Okay, when they transfer momentums. Now, if we were going to calculate final momentum of this system, then we would have to come in here and do 1 kilogram times 8.3 meters per second. And then on the other side, it's going to be 2 kilograms times 1.7 meters per second. And actually, this is negative 8.3 because it's moving in the wrong direction. Okay, so that's obviously just going to be negative 8.3, and then 2 times 1.7, and then 8.3 minus that number is going to give us -5 meters per or kilograms times meter per second. Okay, and these are rounded numbers, so it technically comes out to 4.9. But this shows us that energy, or that momentum and kinetic energy in this case were conserved. Now, we won't go ahead and do math for all of this, but let's at least look at just some different situations here and how that affects things. So let's go back here, let's reset this, and let's go to 3 kilograms now. We'll keep the velocities the same. We'll go ahead and launch these. Now, this time, this one actually stopped. This one shot off really quickly. So again, this one had a lot of initial momentum and then does not have a lot of final. This one did not have a lot of initial and has a lot of final. Again, the math on that will work out, and this is really sometimes can be hard when you're just looking at simulations. I like doing this in the class with the actual carts. But okay, let's reset this one, and let's just do something like this. Let's keep them with the same mass, and let's make this at like -1 meter per second. Let's check this collision out. Okay, so you can see again they flip-flopped velocities there because they have the same mass. Okay, but if they have the same mass or different masses, then that won't work. Okay, so I changed the mass to 2 kilograms. Now notice that those velocities didn't just swap there. Okay, all right, let's go ahead and move on to inelastic collisions, and this is going to be a perfectly inelastic collision. So let's go ahead and set it up as equals again, and so based on what happened before with the elastic collision, where we had everything set up as 5 and -5, 1 and 1 kilogram. This time, if they hit and stick and they have completely opposite momenta, so this one's +5 kilogram time meter per second, this one's -5, what's going to happen when they stick? Are they going to move? Should they sit still? If they're moving, what velocity should they be at? Pause the video, think about that, and then let's look at it. So they come in, they hit, and they stop. Okay, since each object has the same mass and they have completely opposite velocities, they essentially cancel out. So if you think about the initial momentum that was involved here, 5 times 1 is 5, -5 times 1 is -5. The initial momentum of the system is 0. Therefore, the final momentum of the system must also be 0. The only way for that to happen is that those two carts stop. Okay. Now let's look at it if we increase the mass of one of them. So what do you think will happen now when they hit and stick? Are they going to stop? Are they going to continue moving? If they continue moving, which direction and how fast? Should it be 5 meters per second, less than 5 meters per second, or more? Let's check it out. So they hit, and they continue to move to the left in the same direction that the cart with more initial momentum was moving. Okay, so the blue cart had double the initial momentum, just in the opposite direction, which is why this continues to move to the left. And it does decrease its speed because initially the red cart was moving to the right, so that is going to take away some. There, it's moving in the opposite direction. So let's go ahead and do this again, and let's go, well, how about we just do 3 kilograms real quick. We'll show that one, and you'll be able to see that it does increase the speed at which it continues to move to the left once they have connected. Okay, and then we can play around with this, and we can do, how about 3 and 2, and show what happens there. Okay, so again, the one with more initial momentum is going to be the direction that it continues to move. If I switch that, now let's do this. Now the object is going to clearly move to the right together after I have made the initial momentum for cart A, or the red cart, more than cart B. Okay, so the nice thing is that we can actually basically calculate, if I wanted to know, hey, what's the final velocity of these carts going to be, we could do that, so that's kind of what this is for. Last type here, let's look at explosions. So now they're starting together. Let's go with equal masses. They start at 0 meters per second. So what's the initial momentum of this system? It's 0. Neither cart is moving. So that means that the initial momentum, or the final momentum of the system, must also be 0. Well, when I hit this and they shoot off at -10 and 10 meters per second, some people say, well, how can the final momentum be 0? Both carts are moving. They clearly have momentum. Remember, direction. The red cart is moving to the left, which is negative. So -10 kilograms times meter per second of momentum. And the right cart is moving to the right, or the blue cart's moving to the right, which is a positive velocity. So it is +10 kilograms times meter per second. Therefore, they cancel out, and the total momentum of the system is 0, just like the initial momentum. Okay? Now, if we change masses and stuff like that, they're obviously going to move at different speeds, but again, it's still going to conserve momentum here. This one moves, so I doubled the mass, so this velocity gets cut in half. Okay, that should make sense, right? So double the mass, velocity gets cut in half to conserve momentum. How about I triple the mass? velocity gets cut in 3. Okay, divided it by 3. So yeah, you can actually find this on the physicsclassroom.com. This little animation here, simulation, you can play around with this. Hopefully this gives you a good little intro to collisions and the different types and the conservation of momentum.